Welcome to System Devices 1, Week 3 review, what you should know by the end of the week. So in this week's lecture we were looking at binary arithmetic, so how can we build an adder? So we've got our ripple adder here. Hopefully this was quite intuitive. You go through, implement your binary arithmetic that you could do in pen and paper. Do have a look at the adder circuit if you're not sure in the private study exercises to make sure. Then we can start to think about the ALU, so what's inside our arithmetic and logic unit. So we're looking at how we did binary subtraction now. Again, core skill, make sure you're happy with doing subtraction. Two's complement can cause confusions, so do make sure you're happy doing binary subtraction, not just subtraction through the addition of a negative number, as we'll see in a little bit. And also make sure you're happy with two's complement, so make sure you're happy about doing subtractions which generate a negative result, for example. How do you do those in pen and paper? Because that will lead you into the actual hardware that we'll be designing later. So yeah, we looked at our binary subtractor using a half subtractor or full subtractor, then subtraction through the addition of a negative number. Make sure that all is intuitive and make sure you understand why the carry doesn't mean anything, why the carry is ignored if you're doing sign arithmetic, and we have to identify overflows using different techniques, an important bit there. And finally we looked at some bitwise functions, so the bitwise AND, so we saw how we could combine two 8-bit values with an array of AND gates to perform that bitwise operation. And at the moment that may seem a little bit of a why do I need a bitwise operator, but it will become very useful, and we'll see it's actually a key function that we need inside our processor. Okay, to steal a quote from Fight Club, the 3 rules for passing System Devices 1 exam are: do the labs, and do the labs. No, honestly, if you can do the labs, you can pass the exam. It's that easy. So do make sure you complete the labs. And what I mean by that is just don't skim through them and think, oh yeah, I understand that one. Actually do them. Make sure you understand all those subtleties that are embedded in those questions, and you're truly happy regarding the material covered. So this week it should be an easier lab. We're just reinforcing the topics we covered in last week's lecture. So we're looking at encoders and decoders. So the first one, we're looking at that one hot to binary encoder. So we've got one hot value, so you see there's 1, 1, and we're going to a binary value on the output there. Then we go the opposite way around, so the opposite to the lecture material. So we go from a binary to a one hot decoder, as you can see in this table here. Again, for each of these sections, make sure you're happy with the simulation model, so you can see how these test benches test the functionality of each of our circuits. The main design element of this week's lab is task 3. So here we're looking at how can we build a 7-segment decoder, so a circuit that will take a binary value in and produce the correct LED illumination sequence. So you can see here we've got our 7-segment LED, so there's 7 LEDs, and by turning on the correct segments we can display different values. So the key part of this lab, as chatted in the tech review session, is to implement a component using existing components where possible. So we're going to implement a binary to 7-segment decoder, and we could do that just by using Boolean algebra. So we could take that previous truth table and we could convert that into the Boolean equations needed to drive those segments A to G. So what we will have is we will build this component here, so a binary 7-segment decoder, and within there are our 2 subcomponents, our binary to 1 hot decoder and a 1 hot to 7-segment decoder. And the reason why we've implemented this way is building these 1 hot decoders is relatively simple. So all you need to do is identify where you have a logical 1 on a particular output and map that to a particular input state, a particular 1 hot value. The final task in this week's lab is looking at encryption and decryption and component reuse again. So here we have our system, and what we have obviously is the push buttons coming in, going in through our 1 hot encoder, producing a 3-bit binary value that is then displayed by using our binary to 7-segment decoder on a 7-segment display. We take that 3-bit value and we pass it to an encryption block. Encrypts that value with a key and produce a new value, which again we display. We take that encrypted value and pass it now to our decryption hardware block, and again combining that with the same key, we can decrypt it back to the original value. So we have a quick look through different hardware hashing kind of circuit, so kind of just a simple reversing circuit and one based on XOR logic gates, and by using those additional circuits we can encrypt our data, and obviously it's a very simple block cipher. So the second part is this week's exercise sheet. So we're going back and looking at how voltage levels are used to represent our logical 1s and logical 0s in the system, and considering what happens if we get a corrupted bit, a single event upset. As we're looking here at cyclic redundancy checks and parity. So the first one we look at is parity. So we can see how by adding an extra bit we can detect if there's been single bit flips within our data, and again considering what logical circuits can be used for parity error checking. Then we move on to something a little bit more complex. So we look at CRC checks, so cyclic redundancy checks. And again, we're just using XOR functions combined with an initial key or seed to determine what our checksum is. So again, by repeatedly XORing the key and its resultant to the original data, we can generate a checksum, and then we can combine that with our data to see if there has been any errors in its transmission. Finally, we were doing a little bit of subtraction. So hopefully now when you see a hexadecimal representation, so 0x for hex, you can actually see the decimal value or the binary values. So here we've got the value 10 minus 16 as a calculation. So can you do that one in binary or in base 16 or base 8, for example? Can you perform a subtraction in different number bases? So finally we have our robot Cockroach. So this one here, I've kind of slipped a little bit of electronics into this one, so please forgive. Obviously we're not doing electronics in this course here, but we're looking at how we can make a simple compound eye using light-dependent resistors. So basically constructing a potential divider circuit as described here. And again, we're looking at how those voltages can be used to represent logical ones and logical zeros into our system. So here, again, we've got a simple MOSFET transistor, and we're now feeding a voltage into its gate from this potential divider. These two resistors here which generate a voltage source. And you can see this voltage source is the green trace here. So you can see as it increases, it eventually gets to the gate voltage that will turn on this transistor, so turn on the switch, and that's around about 2 volts. So you can see before then the voltage coming out here is being supplied by the voltage supply, so it's going to be 5 volts in this case here. But as soon as we get to the switching voltage of our transistor, so 2 volts, the gate voltage, you can see it turns on and it'll go down to 0, because if that transistor turns on, effectively it's connecting the output to the 0 volts, and the 0 volts is indicated by this ground symbol in SPICE. So can you, from the previous description, work out what this logic gate is? So obviously again N-type transistors, so when you've got no voltage on the inputs A and B, they'll be turned off, and when you put a voltage on here, they will turn on. So what would happen to the output Z? Finally, we've got a simple digital design task where we take those LDR sensors representing the brightness of the various sensors coming in our compound eye, and we want to convert those to a command code. So again, what I'm looking for here is, can you take those existing techniques we've looked at, so Boolean algebra maybe, or encoder, decoder, or multiplexer circuits, and can you produce that output code given a particular input code? And obviously that all comes into the instruction decoder and the logic that will be building inside our simple CPU processor. So linked to that one, part of the open assessment is basically converting a high-level description of what the system should do down into some assembler code, which we'll be looking at in later lectures, so a program. So looking at that CRC calculation performed in figure 3, so can you convert those pen and paper steps that you did when you calculated the checksum into a program, into a high-level description of what it should do? And you'll need those basic programming skills for the assessment. Okay, I think that's where I'll leave it for this week, and I'll see you in the next lecture.